Okay, so picking up part 2 of homework 8-5 here, we'll pick up with question 8. Question 8 is a lot like part B of question 7 too, so if you feel like I rushed that a little bit, maybe come back and look at this question and see if this helps a little bit as well. But they're asking us, to find the total acoustic power output of the source and why. So we're looking for, again, the power output. The other way they may phrase that, as they did in the last question, right, the rate of energy leaving the source, but the rate of energy and power are both the same thing. Right, so they're asking us for the total power output from the source in watts, right? And then they give us a threshold of frequency or of human hearing, and they ask us to go from there, right? So the key concept here is if I want to find the power, the easiest way to find power is if I can find the intensity, because by definition, intensity is power over area. So if I can find the intensity at a certain location to where I can find the surface area at that location as well, then I can find an easy way to get the power. Right, so my first goal then is going to be, can I find the intensity? Well, since they give me the sound level, the intensity level at one location, I can find the intensity based off of that, right? So if I use my intensity level, my sound level formula, right, the sound level, the loudness equals 10 times log of the intensity divided by the threshold of hearing, which is why they gave us that measurement to work with, right? I can solve this equation for my intensity at that location, and then see if I can use it to help me find the power. So they give us 51 decibels equals 10 times log of, again, the intensity over my human threshold of hearing. And I just need to do a little bit of arithmetic, a little bit of algebra to solve this, right? So divide both sides by 10, that gives me 5.1, right? So 5.1 equals log of all of this. And then to get rid of the logarithm, again, the algebraic skill we do need to be very comfortable with is you exponentiate both sides with a base of 10. Right, so I exponentiate both sides with a base of 10. That cancels out the logarithm. And then that leaves me with this, right? So I've gotten rid of my logarithmic function. I now have this. So my intensity then is, if I calculate that value, about 1.26 times 10 to the negative 7th watts per meter squared. Okay, so again, this would be the intensity at that location where the sound level, where the loudness is 51 decibels. Since they asked me for the power, now I'm going to come in, I'm going to use my intensity equals power over area, right? And the key concept is it does tell us that it radiates out uniformly in all directions. So in other words, it's the surface area of a sphere, right? They're telling me it radiates outward in all directions, so it's the surface area of a sphere. The surface area of a sphere is when I use 4 pi r squared, right? So that is the area that I'm working with here. So my intensity of 1.26 times 10 to the negative 7th watts per meter squared equals the power output over 4 pi times the radius squared, and they give me the distance away as 20, right, 20 meters, so 20 squared. So at this point then it's just a matter of solving for the power. Again, the algebra here is hopefully pretty easy, and when you do the arithmetic there, you get about 6.33 times 10 to the negative 4th watts. So there's my power, right, there's my power, 6.33 times 10 to the negative 4th watts. That's how much power is at that location. And that therefore is also how much power leaves the source, because again, the key concept is we're assuming, unless they tell us otherwise, that energy is being conserved, and if energy is conserved, power is conserved. So however much power I have at this location is the same amount of power that left the source a certain time ago. Right, so anyway, make sure you're pretty comfortable with this type of question. It does have some key concepts that you need to be comfortable with as well. Alright, question 9 is basically the opposite direction of question 8. This time they give us how much power is being emitted. They tell us it spreads out again equally in all directions, which tells me I'm using 4 pi r squared. And they give me the threshold of hearing. They ask me to find the sound intensity level 30 meters from the source. And so again, this is basically the exact opposite procedure we just did. The first thing we're going to do is find the intensity at that location. So the intensity at that location is the power divided by, again, 4 pi r squared, the total surface area of a sphere at that location. So the intensity 30 meters away would be our power of 20 watts spread out over 4 pi times 30 squared meters, right? So this is what I'm setting up for my intensity. So when I calculate that intensity, I get about 0.00177 watts per meter squared, or 1.77 times 10 to the negative third if you prefer. And then to find my loudness, my sound intensity level, that's where I'm looking for beta, right? So I'm using my logarithmic function for the decibels here. So I'm taking the intensity level at that location, the intensity, at that location, and dividing it by the human threshold of hearing. and I'm solving from here. So at this point, again, just algebra, 10 times log of this whole function. Make sure that whole thing does end up in the logarithmic function there. We should get about 92.5 decibels of loudness, of sound intensity. So 92.5 decibels is my answer for question 9. Okay, so question 10, aside from the being worded kind of awkwardly and giving you the threshold of hearing twice, right? We don't need it twice, we've already got it once. But hopefully this question's not too bad. You actually do have a couple different routes you could solve this. So they give you the sound level, right? The intensity level of 60 decibels 1 meter away from a person. They then say you're surrounded by 5 such people, and they ask you what's the actual intensity level, right, that we would hear. So what sound level do we hear at that location? So we're looking for essentially what's the loudness, right, at that location if we have 5 people talking instead of 1. So you actually have a couple of choices. You could either first use the 60 decibel intensity level to find the intensity at that first location, right? So I could do this, and I could solve for the intensity at 1 meter away, and then once I have that intensity, I could multiply that by 5, and then plug that right back in and find out what my new decibels would be. The other way, though, the way that I'm actually going to use, just takes advantage of some of the properties of logarithms to maybe make the calculations a little bit easier. All right, so if I want to find my loudness, my intensity or sound level at that second situation, for the second situation where I have 5 people, I'm going to represent it at first just as 10 times the log of 5i over I sub 0. Now I don't know what the intensity of the first person was, but I know that if there are 5 people instead of 1, it would be 5 times as intense, right, instead of 1. So again, what I'm going to do now is I'm just going to take advantage of log properties to break this into 2 logarithms, right? So I know that if you're multiplying within the logarithmic function, you can break it up by adding the 2 logs. So I'm going to do 10 times log of 5 plus 10 times log of the intensity of 1 person divided by I sub 0. Right? And the reason that I do this, so again, all I did was I'm saying this is 5 times this whole quantity here, and I'm splitting it into 2 functions, right? The reason I did this is obviously this is an easy enough calculation. I can just do 10 times log of 5 in my calculator, right? And this ends up being about 6.99, so about 7. And then over here, we actually already know, without knowing the specific intensity, we already know the loudness of 1 person is 60 decibels. So we already know this quantity, no matter what the intensity is, needs to be 60 decibels, right? So in this case, it becomes a very easy algebraic problem to solve. I'm going to take my 7, I'll call that 7, and then add it to my original 60 decibels. So the total loudness would be about 67 decibels of loudness, right? So by having 5 people instead of 2, it increases by 7 decibels. So anyway, making sure we're comfortable with a question like this. Again, there's nothing wrong with solving for the intensity first, but in this case I actually don't need to if I take advantage of my logarithmic properties. Either way, you should get about 67 decibels. Okay, so question 11 here is a good question for just kind of exploring the Doppler effect, and particularly when 2 objects are moving at the same time, right? So we've got a woman riding a bike. They give her the 18 meters per second there, and then she hears a train whistle behind her. The frequency of the whistle is 840, but the frequency she perceives is 778. And then they give us the speed of sound in the air. What is the speed of the train, and what is the direction of the train, right? Is it traveling towards or away from her? Now, the first thing that hopefully jumps out to us is the fact that the frequency is going down, right? It is getting smaller. So let's assume that they're moving apart from each other, right? So we know that the net result is they do get further apart in time. So let's assume that the woman, as she's pedaling this way on her bicycle, right, and then the train is going this way. Because in that instance, we know they're definitely moving apart, so the frequency would for sure be getting lower. The only other situation that would be possible here would be, what if the train was going the same way as she was, but if it was going slower than she was, the frequency would still be decreasing. Right, so we'll consider that in just a second as well. But let's start by assuming that they're just moving opposite directions. Okay, so if they were both moving and they're both moving opposite directions, then I'm just going to account for both of them in the Doppler effect here, right? So the velocity plus the velocity of the observer, excuse me, I'm going to do minus the velocity of the observer there because she's moving away, right? She's moving away from the train in this situation. And then on bottom, I'm going to do the velocity plus the velocity of the source, so the speed of sound in air plus the velocity of the source, right? Because again, I'm saying that the train is also moving away from her. So if we set this up, let's see what happens then when we solve for the velocity of the source. Right, so we know this is 778 equals 840. The velocity in air would be 340 minus her velocity of 18 meters per second, divided by, again, the velocity in air of 340 plus the train speed, which we don't know. So if I look at this, really just one variable in this equation, so just a little bit of algebra to clean this up. And when I solve for that, I get the velocity of the source is 7.66 meters per second. And notice it does end up being a positive 7.66 meters per second. So that tells me the fact that I used a positive velocity of the source here, and this came out to be positive here as well, that tells me that it is for sure moving away from the bicyclist. And let's explore that a little bit more. But this is my answer for part A. Let's just see how we can be sure on the direction. Right, so here's how I know the direction is accurate. What if the train was moving in the same direction as she was, but it was moving more slowly? Because we actually can definitely see that the train is in fact moving more slowly. Well, I would still set this up as 778 equals 840. The numerator of my expression representing her velocity would be the exact same thing. So 340 minus 18, she's still moving away from the train. So that would still be true. Right? The only difference, the only thing that would change here would be I'd be subtracting my velocity of the source on the bottom. Well, if I solve this, I'm going to get the exact same answer, except this time I'm going to get negative 7.66 meters per second. And if we think about that, why does that tell us that it's still got to be moving away from the person, the bicyclist, right? And the reason for that is this definition here is saying that it's moving towards the bicyclist, right? We're saying that it's a velocity that's going towards the bicyclist. So that's Vs we're defining as the velocity toward the bicyclist. Because we get Vs to be a negative number, we have a negative velocity towards the bicyclist, which in other words means we have a positive velocity away from the bicyclist, right? If the velocity going towards the bicyclist is negative, then we're not moving towards the bicyclist, we're moving away from it. Okay, so I don't mean to confuse you by that, but I do want to illustrate that there is just one answer here. It is 7.66 meters per second, and it is directed away from the bicyclist. All right, so then part B, once we've established that, hopefully part B is pretty easy. Part B asks us what would be the frequency heard by an observer standing somewhere between the train and the bicycle. So again, here's the train going one way, here's the bicyclist going the other way, here's some observer just standing there, right? We want to know what frequency does the observer hear based on the train's whistle. So again, this question becomes pretty easy because I don't have to worry about the bicyclist at all for part B. Now that I know the train is moving away from the bicyclist, I know the train would also be moving away from the observer. So I would be adding in the denominator there, and I know the velocity to add, so it's just a matter of plugging it all in. Right, so 840 is the initial frequency, 340 is what we're using for our speed of sound in air, and then the 7.66 that I've solved for being the velocity there of the train. Right, so when I calculate this, obviously it should be a little bit lower, and in fact it is. 821.5 hertz is more or less what I get, so 821.5. The frequency that the observer hears from the train. Right. And I think I'll go ahead and stop this part of the video here just so I have enough time to go through 12 fully and then wrap this up with question 13 in the third part of this video.